Hello, and thank you for joining me. You're here with Data Science Teacher Brandyn, and we're going to go over the extra trees ensemble method in sklearn using Python. And so extra trees is the extremely random trees, which is very much related to the random forest. And the big thing, what it does is it's a little bit more random. It's extremely random. And what it does is it's adding in when the decision trees inside the forest are splitting, what it does is it adds an extra layer of randomness in that the threshold boundary for kind of where the split happens is randomized now. So it's not just a set boundary, it can be random inside of which one it determines to do a split on is a little bit more randomized. This makes each tree more different, which can impact the effect of the ensemble method. The concept of many trees voting together can give you a better average, can give you a better vote as long as they're different but still provide information. Okay, so we'll go through today. I'm going to compare this one as we go through today with RandomForest, looking at the comparison with extra trees, extremely random trees. Okay. So they're both from the ensemble method, RandomForest, and we're going to do a regression problem and then extra trees as well. Okay. So importing this is the concrete data set, and it's typically predict the CSMPA, which is the strength of the concrete. To make it a little bit more challenging, we're going to predict something else. So I'm going to predict the water in this data set. Don't want it to be too easy of a data set, right? And this is a pretty famous one. You might have seen this one before. So here, just quickly exploring the distributions of the data set. I noticed a few things as we were going through this, and one of the biggest things is I wanted to bucketize this really weird distribution for age. So I did bucketizing into 4 different buckets, and I'll one-hot encode that in the next one, pretty easy. I also noticed in the slag, fly ash, and super plasticizer, no, concrete, sorry for my pronunciation if that's a little bit off, you concrete specialists. And here what we're going to do is we're going to do supervised plaster, and you see there's so many values here. 1, so, or sorry, 0. So the thing about 0 is our model can't use that. 0 times anything is 0, right? So it's not usable by our model. It seems like there's an event going on here. This is when a certain condition is happening, maybe to the concrete or something. I don't really know, but because this is 0, our model wouldn't be able to use this at all. So because this might be an important impact or a suspicion, what I did was I one-hot encoded for when the super plasticizer, the slag, and the fly ash, it was the same characters in those 3. When I noticed those, what I did was I would one-hot encode that just for a variable that represents when this is 0, everything else will be 0. But when it's a 0 here, we're going to have a 1 in this column. So our model now has a way to push off this value. And that really very kind of light pre-processing, not to spend too much time on this. It did really work well. So slag, when it's equal to 0, this creates a true and false column, but we multiply it by 1 here just to change that from true to false to 0 to 1. Okay, so do the same thing for all these. Really easy pre-processing in this one today. Okay. And you can see there are a lot of values in the 0 column there, right? So it made a lot of sense to do this. Doing my train test splits, creating my features, a list of my features, my target, X and Y, and then putting X and Y to the train test split. Gonna do PCA and standardization, so standard scalar, and then PCAs right here. Really just good pre-processing techniques. So when we look at just the default settings of RandomForest and ExtraTreesRegressor, see by default, the ExtraTreesRegressor did 93 on the test set and 88 on the test set for RandomForest. They're both very good models. Really, out of the box, quite a bit better for the ExtraTreesRegressor. And let's see if we can pre-process this, tune the hyperparameters a little bit more to improve this model. Okay. So really, and I just want to highlight, well, what's the difference? The main difference as I discussed up above was that the randomness, that's really the biggest difference, is that the random forest, has lots of randomness versus a regular decision tree. There's a little bit of randomness in what features, are available for each split. Extremely randomized trees have that as well. They also allow or add an extra layer of randomness that basically determines the threshold of where that split is going to happen. That is randomized. Okay, so that's really the big difference, and that's really the main difference between these two. They're from the same offshoots. They're very similar ensemble methods in that sense. They use bootstrap aggregating, just like the bagging ensemble method as well. Okay. So here, just going through these, I'm going to look at different estimators here, and we're going to 5 to 500. So really getting a complete grouping of those, putting those into the estimator, changing those for each one, and fitting the random forest, then the extra trees, looking at the line plot for 2 of those, and then I'm pulling out from the estimators using numpy.argmax. The best test score, I'm going to pull out what the estimators are. This np.argmax gives me the index position of where this happens, so I can use that then to pull out the number of estimators that was the best. Okay, so here we got the extra trees, 95, and random forest was 290. Okay, quite a big difference. And you see here that the test of the extra trees and the test of the random forest, really the extra trees always seem to be performing not substantially, but consistently better than the random forest. Okay, and the kind of shaded out versions, same colors are the train, and then the darker colors are the test. Just make it a little bit clearer. Really want to focus on the test, but it's always helpful to understand we do have some overfitting, so we would be concerned about that. Really here I was just trying to not worry so much about the pre-processing for this, just worrying about the differences in the extra trees ensemble method. Okay, so now we determined the best estimators. I use those ones here, and now we're going to try and max depth. So going from 2 to 20 and getting a sense of those. So we found extra trees, max depth of 19 was the best, and random forest was 16. Okay, so going through there, add those to our models in the next step, and we're going to do max features then. So what are the amount of features that are considered at every split, right? So it can be very helpful. Extra trees here actually worked out the best when we used 94, okay? And we went all the way up from 10% to 100% by 1%. So testing kind of the whole range here. And random forest actually works best when we're only considering 55 at every split. And we don't have that many features, so it's kind of cutting it in half. It's a pretty small amount of features, truthfully. Okay. You don't normally see this from random forest. You can often see it to be a much higher number. So I would say maybe a little bit untypical in this data set. But still really see here, as we added in more for random for extra trees, it always seemed to do consistently better as we added in more of the variables for consideration. And really random forest, it didn't change it too much, surprisingly, as you went through, and you actually see it at a smaller amount right here. It was quite a bit better. Okay. And then trying the bootstrapping. So this is using bootstrap aggregation to build every single decision tree. If you know anything about hacker statistics and how we can use hacker statistics to simulate regular statistics and hypothesis testing, bootstrap aggregating you would think would work because it would make then every tree built on an independent data set. Bootstrap aggregating is where you pull out a row, kind of write down the values, you put the row back, so when you sample again, you can draw that row twice or maybe miss that row, miss some rows. This makes independence in the new data set the replicate, and that we would think then that because this can be used in hypothesis testing, even bootstrap aggregating, you would think that it would work well here. It actually seemed that it didn't. So we actually saw that the really only a true and false value here that we went through, so true and false. And so trying 0 or 1, and you actually see that when we did bootstrap aggregating, it was significantly worse, which was kind of a surprise to me, truthfully. But for that worked the same for both trees. Okay, and it had a bigger impact on the extremely random trees, but still an impact on the random forest as well. So trying those again and getting our final scores here, we see we were able to get the random forest on the train set up to be quite good, and then getting it at a 90. I was not able to improve, and that doesn't mean you won't be able to, but I wasn't able to really improve the ExtraTreesRegressor. It's still our best at 93%, which is a really good R-squared. Was not able to improve it out of the box though. And so there might be involved more pre-processing. You might be happy with a 93% in terms of your prediction problem, maybe concrete, the water and the concrete 93% is a satisfactory score for that type of prediction. Really depends though. Okay, so Thank you so much for joining me today, and I will see you for the next video.